So good afternoon, everyone. Welcome to another session of the CITA seminar. It's my pleasure to introduce you to Aditya Vijaykumar, who's going to be giving a seminar on probing the host environments of compact binaries. He's around, so if you're looking for a meeting to him, just contact him.
Okay, thank you. Thanks all for coming. I know there have been at least 3 seminars on gravitational waves in the recent past. I think the last 3 seminars have all been on gravitational waves. So I'm the 4th in a row. I'll hope to live up to the hype. Okay, so just a small introduction. I think most people have heard about gravitational waves here, but just a small introduction to people who have not heard. Gravitational waves generated by these compact binaries. What I mean by compact is sources of objects which are really, really dense and compact, like black holes, like neutron stars. These are of course, stellar depths. And we've detected gravitational waves from the mergers of these objects. So these objects form binaries, and they lose energy and angular momentum through gravitational radiation. They shrink and eventually they merge. The signal from these compact binary sources have this very characteristic chirping feature. What I mean by chirp is that the frequency and the amplitude of these signals increases as time goes on until this object merges, and then the final object that is formed just basically radiates away its perturbations and rings down. So as you can see in the signal, the amplitude is low at earlier times and large at later times, and the frequency is also low at earlier times and large at later times. And this characteristic feature is called the chirping feature. Right. Typically, we can detect with current LIGO, Virgo, Cabra network of detectors, we can detect these binary black holes. There's basically a compact binary with 2 black holes in it, up to a redshift of roughly 0.5, even more, but depending on the mass of the black hole, which is about 3000 megaparsec of luminosity distance. And binary neutron stars, because they're less massive, we can detect them only up to a redshift of 0.05, which is pretty nearby, up to 200 megaparsec. Right. So that's a very quick overview. I think people have seen this plot way too many times, but what I really like about this plot is that, so this is a plot of basically all the binaries that we've detected so far. So it's basically two black holes merging to form a larger black hole, as shown in each of those dots. What I find really interesting about this plot is that just about 9 years ago, we had 0 points on this plot. And so just in about 8 to 9 years, we've detected about 100 of these things, and the observing run, the 4th observing run of LIGO Virgo Cobra is on. It's in the middle of a commissioning break right now, but it's still on, and we are detecting even more as time goes on. Also, with one eye toward the future, there are plans to build much more sensitive gravitational wave detectors on the ground, such as this Cosmic Explorer, Einstein Telescope, etc. These are expected to have a very high distance reach, and hence many more events. So on the right, I'm showing the typical horizon, what we call the horizon redshift of these mergers as a function of mass. As you can see, if you look at the ET plot, for instance, you can see that roughly 40 or 50 solar mass black holes, you can see up to a redshift of 100. Now, there might or might not be black holes, binary black holes at a redshift of 100, but if there are, due to some reasons, say primordial black holes and so on, we can detect them. So these next generation detectors are extremely exciting because not only will they allow us to probe very far into the stretches of the universe, but also we will have like a very large population of binary black holes and binary neutron stars.
Now,
yeah.
This plot here, is showing the orange curves that
there's
comparable sensitivity at 1,000 solar masses at present and at 20 solar masses. Is that?
That's roughly right, yes. The current detectors are most, I think A-LIGO is the most,
But we're not getting close to 1,000 solar masses in actual detections.
Yeah, that's because this does not take into account the actual rate, underlying rate of those detectors. So it might be that 1,000 solar mass black holes are just never born in the universe. And so, yeah, that's the way. But if there were, we could maybe detect them at up to redshift of at 0.1. So, yeah, that's right. Yeah.
I mean, I'm hesitant of asking this question, but it goes on to redshift 100 there.
That's
what
right.
objects do you have at redshift 100?
Yeah, so as I said, this plot does not take into account any astrophysics really, so there might or might not be black holes at redshift of 100, but for instance, people think that, black holes formed in the early universe could form binaries, and if they merge at redshift of 100, we could see them.
Yeah, very interesting. Okay.
Okay, these are the ground-based detectors. These roughly operate in the roughly 10 hertz to 100 hertz frequency regime. But there are other proposed detectors in the future, such as the millihertz detectors. You might have heard of LISA. This is a detector in space. There are proposed decihertz designs called DECIGO, LGWA, LIDAR, etc. And there are detectors also proposed in the kilohertz regime. Now, the kilohertz detectors especially will be sensitive to the post-merger regime of binary neutron stars, which is a really exciting prospect, and it will allow us to probe things like the hot equation of state. But again, all these things are still in the planning stages, except LISA, which will fly for sure. But all the other detectors are still in their planning stages. And
what's the essential technological innovation that's needed to really hit the kilohertz regime at a significant rate?
So from what I understand, it's nothing really different apart from the fact that you sacrifice on sensitivity at the lower frequencies and make the sensitivity better at higher frequencies. You basically tune the detector to be that using these fancy techniques that the detector side people call frequency dependent squeezing. Okay, so this is what the data from our detectors looks like. It's a noisy sort of time series, and this is for GLB 150914 from the Hanford detector. And once we have this data, we can compare them to theoretical templates of gravitational wave emission from binary black holes or binary neutron stars, and sort of get a posterior distribution on, say, the primary mass and the secondary mass of the merger. What I mean by that is, so for people who are not aware, this is basically, you can think of these bits as typical error bars on our measurement. And as you can see, these are pretty uncertain measurements. Like there's a error of roughly 10 solar masses in the secondary masses, also in the primary mass. Right. So when people draw those dots on that stellar graveyard plot, they're not precise measurements. They are very uncertain measurements, as I've shown you here. Right. And once we have many such uncertain measurements, what we can do is we can correct for the selection effects. What I mean by that is correct for the fact that we are supposed to observe more massive mergers than less massive mergers, or mergers more nearby than mergers far away. We can correct for those selection effects and sort of figure out what the distribution of, say, masses that we are observing is. So this is the underlying distribution of masses of black holes in the universe. So these are constraints from the most recent LIGO-Virgo collaboration paper for the population properties of black holes. And as you can see, this curve is already sort of interesting, especially around this 35 solar mass peak. It's not a very confident peak yet, but if it is confident, we know that is basically, I mean, people think that it might be the parent stability supernova mass gap, but there have been discussions in the literature which say that it might not be the parent stability supernova mass gap. So things are pretty open here, but one thing is for sure that we are starting to see features in the mass distribution of gravitational wave pairs. You can ask the same questions for the distribution of mass ratio Q. So Q is just M2 or M1, the mass of the smaller black hole divided by the mass of the larger black hole. And as you can see, more black holes prefer being equal mass than unequal mass. The same question can be asked as to what the distribution of binaries is as a function of redshift. And you get something like this, which is which basically shows you that things are increasing as a function of redshift, roughly following star formation rate. Okay, cool. So these ensemble properties of gravitational waves, such as their masses, spins, redshifts, mass ratios, etc., can be compared to astrophysical expectations and can be used to answer very interesting questions, such as where do these binaries form and go? This is an open question. I don't think we have a definitive answer for those questions, and there are a variety of models proposed for this. For instance, maybe these binaries just form and grow in the galactic field without really interacting with other third bodies in the process. Maybe they are in dense stellar clusters, such as globular clusters, where they're undergoing interactions with other stars and black holes in the globular cluster. Maybe they're in AGNs, and they might merge because of the interactions with the surrounding gas. Something else, we don't know yet. But we can always forward model things using some prescriptions with these models, and then derive distributions of these masses, spins, redshifts, etc., from those models and compare that to data. It can also, as I said in the previous slide, it can also tell us these binaries might be able to tell us about stellar collapse details as to how supernovae behave, equation of state of neutron stars, and many, many more. And we have a large presence in CITA doing these kind of things. Okay, so what I want to talk to you today, what I want to talk to you today are basically two works, the first of which is a work that I put out a couple of months ago, which is in collaboration with Maya, who's here, Sushmita, who's a professor in India, in Pune, and Daniel Holz, who's a professor at Chicago. Okay, so this deals with inferring the host galaxies of binary black hole events. Binary black holes form and evolve in galaxies, or so we think at least, that they form from stellar collapse, stars form and evolve in galaxies, so on. But then one question that we can immediately ask after you make that statement is, do they form and evolve in currently star-forming galaxies? Do they form and evolve in massive galaxies? Or, sorry, do they merge in star-forming galaxies? Do they merge in massive galaxies? Or something else? However, because we cannot accurately localize our sources well on the sky, you can't answer this question on an event-by-event basis. So you can't take an event and just say, oh, okay, this is the host galaxy that it lied in, because in the typical localization volume of gravitational
We're back. Sorry about that. Didn't know what happened.
So we just okay, thank you. So yeah, sorry for that interruption. But yeah, the redshift evolution of binary black holes, the rate of binary black holes measured from the GWTC3 data, should already sort of shed light on the BBH host galaxies. Right. Okay, so this is a cartoon way of thinking about the whole problem. A set of star-forming galaxies will evolve consistently with the cosmic star formation rate density. So you had more star formation in the past than you have right now. So it will increase with redshift. So this blue line here is basically how a set of star forming, the number density of galaxies weighted by the star formation rate, how that would evolve as a function of redshift. I'll refer to these galaxies as SFR-weighted galaxies in the rest of the talk. On the other hand, if you weight galaxies by their stellar mass and ask what that distribution looks like, that will decrease with increasing redshift. And that's just a byproduct of the fact that galaxies form their stellar mass over time. And you have more mass in the universe right now, more stellar mass in the universe right now than you had in the past. So this is that curve. And these black lines are basically, you can think of these as some error regions of our inference from the latest gravitational wave transient catalog. And as you can see, and as I've shown you on the last slide as well, most of these black curves actually prefer an increase of the rate with redshift, which means we can already state that something like the stellar mass weighted set of galaxies is ruled out as a complete description of the hosts of binary black holes. So what we do is we take a very, very simple mixture model. We say that, this is just a cartoon exercise, by the way, and we take a simple mixture model and say, galaxies could either be coming from this kind of evolution or this kind of evolution, and then we try to constrain what the mixture fraction is. So this is a typical assumption used in, for instance, the transients literature, like the electromagnetic transients literature, like short GRBs and FRBs, and also some other work which is done by Sushmita, Maya, etc., in context of gravitational waves as well. And then, exactly, so then what you do is then we compare these black lines with these mixture model that I mentioned and say that, purely stellar mass weighted galaxies are ruled out. And the maximum contribution of such galaxies which follow this kind of rate evolution would be 43% at 90% confidence.
Isn't it also true that the accretion rate of AGN is increasing even more rapidly with redshift?
That's right.
Star formation.
That's right. Yeah.
So can you, if you just make a naive scaling of, say, AGN-centric black hole mergers with AGN feeding, right?
Yes.
Set a constraint on that.
Yeah. And I've not done that. That's something that I plan to do. I want to be more careful about that because, those claims are much more, fancy to make, I guess. But yeah, that's precisely the power of this. I don't think this was appreciated much in the community, and now that I think we understand this much better, I think the natural next step to do would be things like you suggested. Yes. Thanks for the question. Okay. So that's more of a cartoonish picture thing, but it's still actually, even though it's a very simple mixture model, we still can see that not all of these gravitational waves don't come from these really massive galaxies, just from these really massive galaxies. So what we do is we try to do it in a more proper manner, say. So one thing that we have to include in that is the fact that the binaries that we see in the LVK right now might have actually formed much earlier as compared to the redshifts that we infer. And the reason for that is there are many processes, stellar processes, gravitational wave-driven inspiral processes, etc., that go into taking a binary from being far apart to it finally merging and we seeing it in the gravitational wave detectors. And this is typically this time between the formation of the binary and the merging of the binary is typically referred to as the delay time. And you can think of this roughly as a time taken to shrink the binary by gravitational wave emission and other processes. So a binary could start off at, say, a redshift of z equal to 4. Maybe it formed black holes then. But because they're far apart, it will take a lot of time to spiral slowly and then come and merge. And maybe they merge at around z equal to 1. And the time difference between z equal to 4 and z equal to 1 would be the delay time of the binary. Okay. And people there have been expectations of what the delay time distribution should be from simulations of these formation channels. And this is one example, for instance, from isolated formation channels for binary black holes that evolve in an isolated manner throughout the galaxy. And there are different channels that say, maybe it is the distribution of time delays is 1 by t, or maybe it's t to the minus 0.35. Basically, this is an unknown quantity and it needs to be constrained. And as you can see, if we constrain these, we also put sort of constraints on the formation channels. This is only for two formation channels, the common envelope channel and the stable channel, but then you can also do this for globular clusters. I know Claire, for instance, has been working on doing something like this for globular clusters. You can do it for any other formation channel.
What is tau min?
Right, should have explained that. So the tau min is basically the minimum time that it takes for so it's basically, you can think of it as a hyperparameter of the distribution. What it physically signifies is the minimum time it takes for a binary to merge. So this could, think of a binary that is born at the closest separation. This would correspond to the time it takes for it to merge, for that closest separation binary to merge by gravitational wave or some other process as well.
Aditya,
Yes.
time 0, that's when the black hole binary is formed, not when the stars form.
You could think of both, but the thing is, these are massive stars, so they actually have a very short evolution time scale as compared to the
Compared to 10 million years?
yeah.
And there's no like hierarchical forming of these black holes.
What do you mean? Like two black holes merge and then it meets a third black hole and form stuff like that? Yes, those could happen, but they for that to happen, you need other black holes around when this first black hole merges. And so, things like globular clusters, these things can happen inside our full mergers can happen. But we don't, these formation channels do not take that into account. Okay, so we then thought of applying a physically motivated prescription, which uses galaxies and corresponding delay times. So already from the redshift evolution of the merger rate, we can actually constrain the parameters of this delay time. So this is the TD min or the tau min that I mentioned on the last slide, and this is basically the slope of the power law time delay distribution. And we can just use this model, parameterize the merger rate as we saw of binaries in GWPC3 by this kind of function which depends on a formation rate and the delay time. This formation rate is just taken to be the formation rate of stars in the universe, so the cosmic star formation history. And for different choices of the time delay distribution, P of TD, you get different expectations for the R of Ts. And then you can compare this to your data and just constrain the parameters of this P of T. And as I said, I parameterize the time delay distribution model by a minimum time delay at the power of exponent alpha. And doing all this, you can constrain that minimum time delay to be less than about 2.2 gigayears, and constraint or put an upper limit on the tau min to be 2.23 gigayears, and the alpha has to be lesser than 1.55. So these things we can actually say already from current data. And this is consistent with other recent works which have tried to do basically the same thing.
Less than minus 1.55 mean flatter than?
Flatter than? Sorry?
Because your example said minus 0.35 and
That's right.
minus 1.
Yeah, so we know what we can try to say is that it's definitely not minus 1. And so this minus 0.35 is flat and minus 1.55 would be sharper. This is essentially saying that the time delays are low in the population because the
Very steep.
yeah, the functions are very steep and even the minimum time delay is low.
Steeper than those.
Yeah, steeper than these. Okay, so if you had, so as I said, the physical picture that you should have in your mind is galaxies form stars, and then those stars evolve to form binary black holes and eventually merge. And if the delay time is short, the galaxies haven't evolved too much, while the binaries have already merged. But if the time delays are long, especially on the orders of gigayears, the galaxy which actually had formed those stars might not be forming any stars at the epoch where the events actually merge. So if you have low delay times, then most of the host galaxies would be star forming, as it's shown in this figure. As you can see, there's more support for galaxies to be star forming, so the star formation rate have high star formation rate and low star formation rate. Right. But then when you have high time delays in the population, you have support for very massive galaxies to be your hosts. And this is just due to the fact that you now, all the galaxies that actually form the progenitor binaries are sort of quiescent by now. And so this is the case when what happens when you have large delay times. Right. Okay, so what we do is we use this universe machine models of galaxy evolution, which models the star formation rate and mass assembly history as a function of redshift of galaxies, of mock galaxies. And instead of using first principle physics, what this universe machine model does is it populates galaxies into dark matter halos. So it forms the galaxy halo connection based on, to make it consistent with a large set of actual observational data. So basically you can think of this as creating a galaxy or emulating a galaxy formation procedure, but to where the cost function is it being consistent with a large set of observation. Right. And then what we can do is we can take each individual galaxy in this sort of mock simulation and track every galaxy star formation history with a delay time. And this is basically what we are doing in the mathematical form. And this, mind you, this is the same equation as the equation that I mentioned in a few slides before, except that that was written on a global level or an integrated star formation history across all galaxies, whereas this is written on a per galaxy level. Right? So the merger rate of galaxy of binaries in a galaxy at redshift z naught would be the formation rate of stars at a time which is t of z naught plus td, and then you have some time delay distribution. You convolve it with the time delay distribution. And then you can, once you do this procedure for each of your binaries, you can now plot histograms of galaxies weighted by their merger rate. And so this is what you get.
Could you go back to the first slide? So this is assuming that your binary black holes are the products of star formation. So you have the massive stars are in binaries, and that's the binary black holes that you're seeing.
Yeah.
But that's a very difficult formation channel, isn't it?
That's a very difficult formation channel.
For binary black holes?
No, it's not. I mean, like there are simulations. So basically, you're basically trying to say that just massive stars collapsing somewhere in the galactic field.
Just pick out the binary.
No, so there are simulations in the community. I mean, of course, the rates that derive from these simulations are still uncertain, but these can explain like the detected LIGO merger rate. So it need not necessarily be in, say, a globular cluster environment where it has these n-body interactions. Okay, so then you can plot the histogram of galaxies in this two-dimensional star formation rate and stellar mass plane, and basically I think the color represents the the number of galaxies that can be there, number of host galaxies in each of these stellar mass star formation rate cells. And as you can see, mostly star-forming galaxies are preferred. There is some small I think the colors are not very visible there, but these are really dark reds on the star forming branch, and these are less light reds. So what that means is that there is more support for the current binaries to be in star forming galaxies than in quiescent galaxies. Right, and also this is the log of PDF. Right, so I can just also that was a two-dimensional histogram. I can also plot the one-dimensional histogram, and this is where things are a bit more clearer, I think. So this is a set of galaxies weighted by star formation rate. So you take all galaxies at a certain redshift. In this case, it's redshift of 0.2. You weight them by the star formation rate and plot a histogram. You do the same thing by weighting them by stellar mass, and you get this orange histogram. Now we take all these we take the weights that we derive, or the merger rates that we derive from a prescription, and plot those in these green bands. And as you can see, these green bands, you can think of these as observational uncertainties, the width of the band. They are more consistent, I mean, they're consistent with star-forming galaxies than a set of galaxies which is just weighted by their stellar mass. So this is the histogram of the stellar mass. I mean, of course, for the star formation rate, it's the same picture, and also for the age, the mean stellar age of the galaxy of these merging, which are the hosts of these merging binaries. You can also ask what the typical magnitudes of these are. So what you do is you take the star formation history of each of your mock galaxies, generate mock spectra, and ask what the B band magnitude and the KS band magnitudes are. And again, you see that things are more consistent with star formation rate rather than stellar mass. And this is not surprising because all these quantities are just derived from quantities that I showed on the last slide. Right, so just to quickly summarize, the redshift evolution of the binary black hole merger rate inferred from our latest catalog already sheds light on probable host galaxies. Purely stellar mass weighted sample of galaxies, which should be purely stellar mass weighted sample of galaxies, is ruled out. We developed a framework to also combine delay time distributions and galaxy star formation histories to constrain the set of host galaxies. And these methods that we use and the parameter space of host galaxies that we derive could be used to weight galaxies for the measurement of, say, the Hubble constant using gravitational wave sources.
So how much more in the way of statistics do you require to be able to begin to probe second parameters like galactic nebulousity?
So what happens with heretic?
Because, I think lower mass galaxies tend to be more, as experts chime in, tend to be a bit less metal rich than the movie.
That's right. So Maya already has a work which includes this metallicity variation in the universe.
I'm not surprised, but the question is more, how much data do you really require to begin to untap? Because that's very relevant for the degenerates, right?
Yes, exactly. So what we essentially do in the gravitational wave hierarchical inference is fit this rate evolution with a power law, and that's 1 plus z to the kappa. And kappa is right now consistent with its 2.5 plus minus 1.4, I want to say, or 1.5 or so, and that uncertainty goes down as root n. So we have 100 events right now. If we have 300 events, that's down by a factor of root 3, which means it's 2.5, say, plus minus 0.7. And then that structure might be able, of course, you get better measurements of, say, the metallicity and stuff like that if you have that. But the real, I guess, constraint on metallicity will come from real future detections when we start probing the peak of the star formation rate, the global peak of the star formation history.
Also, of course, there's more information that you're folding over here, which is the mass distribution. And so with more data, you would actually get mass distribution as a function of redshift.
Exactly, yes, even that too. Yes, so right now we can't say anything much about that. We can't
It's
say.
probably easier to get than metallicity.
That's right. So you can't get metallicity directly. All you can do is try to, assume, say, delay times are short and try to, so the metallicity specific star formation rate would have different peaks at different redshifts depending on the metallicity. And once we start probing, say, redshifts of 1.5 to 2.5, we can now start placing constraints on that. But that's still maybe 5 years down the line. Yes?
It's one this is a nice thing. If the detectors continue to get more and more sensitive, the bulk of your catalog is at slightly higher redshifts, like distances. So you can actually get faster convergence than 1 over root n on this redshift evolution parameter. Because you'll get the same fractional uncertainty in distance, but it's much further. So you'll get a better picture of redshift. So it's not just with the detectors stay the same sensitivity, you turn it around 1 over root n. But there's this nice thing that the detectors also get better, then you can get faster convergence.
That's right, yeah, and thanks for that. Yes. Okay, so, sorry, I'll just stop once here and ask if there are any more questions because I still have 20 minutes and I think that's now for the last part of my talk. Okay, no questions. Then I'm going to switch gears a little bit and talk about another project of mine which I just completed before I came to CITA. And this is basically probing the line of sight acceleration of merging compact objects with gravitational waves. I talked about this at last week's tasty seminar, so apologies for people for whom this is a repeat, but I hope I'll give a little more insight than I did last time. So this is with collaborators in India, and also I have written other papers with collaborators at Northwestern and again India. Right. So the basic principle is this is binary black holes. Okay. These are the wiggles that I showed you earlier in the talk. What you can do is now ask what the frequency is as a function of time. What the frequency of these waves that you're getting, the frequency of the data that you're getting is as a function of time. And you get these kind of plots. And this is what the gravitational wave chirp is. The amplitude, as in the brightness of this plot, is increasing with time, and the frequency is also increasing with time. Right? So these are the chirps, as I guess you very well have seen many times before. And this is the chirp of binary neutron stars GW1717. Notice that this chirp is really long. I know I've not put the time axis, but believe me, they are really long because these are lower mass events, and lower mass events stay in our observing band for longer than high mass events such as black holes, 15 or 9, 14. Yeah. Right. So what in gravitational wave detectors, what we really measure the best is actually the slope of this curve. And so the slope of the curve as a function of time, right? And now you can take that slope of the curve and the frequency as a function of time and construct a mass scale out of it. And this mass scale is very evidently known as chirp mass. So I take the slope of this curve, which is f dot, which is a frequency versus time curve, divided by some frequency to the power, raise it to some other power, multiplied by a fundamental constant, and then, and lo and behold, I get something called the chirp mass. And this chirp mass, the measurement uncertainty in this chirp mass is roughly for an event like say 0 to 17 or 17 is of the order of 10 to the minus 5. So this is the fractional uncertainty in the measurement of the chirp mass. And the chirp mass can actually be related to the intrinsic parameters of the binary. That M1, M2 are just the masses of the binary, of the objects in the binary. It's some pure combination of these two masses. Right. Okay, so we measured the chirp mass really well, 1 part in 10 to the 5. That's the take home message. Okay, but right now we have not considered that the binary, we have not considered whether the binary is moving or stationary. We've actually considered that the binary is stationary right now. But if the binary center of mass actually has a velocity v, the gravitational waves will get redshifted. Similar to how light gets redshifted if it has a velocity v. And let's ignore cosmic expansion for now. What you'll see essentially is a Doppler redshift is v over c, right? So if the binary has a center of mass velocity v, you'll see a Doppler redshift v over c. And this is just basic redshifting. The frequencies will get redshifted. The frequency dot will get redshifted by an extra square factor, and this is just due to the fact that there's a time dilation component on top of just the frequency. Okay, cool. So all fine here. And now if you put this f and this f dot into that formula for the mass scale, what you'll see is that the mass that you'll actually see in the detector is the actual intrinsic mass times 1 plus Doppler redshift. So this is called, we refer to this in the community as the redshifting of mass, although it's not really the mass that is getting redshifted, it's the frequencies that's getting redshifted. Right. So if you have a constant velocity, the thing that you measure in your detector will still be a constant, right? Because it's a constant in the intrinsic parameters, and then you multiply it by another constant, which is just v over c, you get a constant chirp mass that you see in your detector. And then this constant chirp mass that you see in your detector, you can't measure the z dot separately from the intrinsic parameters because they're degenerate quantities, and there's nothing in the detector that can tell you whether it is moving or not. So you can't really measure Doppler velocities just from the gravitational wave. constant Doppler velocities. However, if you have an accelerating binary, you have a time varying velocity, which means the Z Doppler actually varies with time, which means the chirp mass actually varies with time that you see in your detector. And because you can measure the chirp mass really well, you can also measure variations in the chirp mass really well when you see it in your detector, and hence you can measure this time variation of the Doppler redshift, or in other words, time variation of the velocity or an acceleration. Specifically for a 170817 like signal, if A is the acceleration, t is the time for which the event is in the band of the detectors, and c is the speed of light. If this quantity is greater than 10 to the minus 5, this quantity is dimensionless by the way, you can actually measure it. This translates to an A by G of greater than 3. So if this condition is satisfied for a 170817 like signal in present day detectors, you can actually measure the acceleration. I know. So this is basically, that is an intuitive way of looking at things, but if you do the calculation and crank things and write things as a expansion in this V over C, so this V is just V over C, you see that you get a really large expression. I won't bore you with this, but I'll tell you that, if you add that extra phase difference, so that's basically changes the gravitational wave phase as a function of time or frequency. If you add that onto just a non-accelerating binary, you see that things have begun to dephase. So what I've done here is I've generated a waveform with acceleration and without acceleration. So generate a signal both with and without acceleration. I've aligned them at the peak at t equal to 0 when they merge. And as you can see, especially if you go way back here, you'll see that these waveforms aren't the same at especially early times. And this means that there's some dephasing going on in the signal, and this dephasing is happening due to this extra acceleration that I mentioned. And since we can actually detect these dephasings, we can actually detect acceleration. So there's another way of seeing that we can actually detect accelerations or measure accelerations. But then, how do you actually give a binary some acceleration? And this is not very difficult to do. Acceleration motion is really common in astrophysics, and binaries, whether they're near supermassive black holes, in globular clusters, or even in the galactic field, would have some kind of acceleration because they're in some orbit, in some potential, right? And as I said, where binaries form and grow is an open question. So if you measure this acceleration, you can sort of try to now say what kind of environments these binaries form in. So just before I proceed, I've just given some typical values of acceleration here. So if you just populate stars in a galaxy like the Milky Way, following some stellar mass profile, and ask what the typical value of acceleration for such binaries would be, that would be really small. So I'll always quote acceleration in units of A by C, which will have units of inverse second. And so for just galactic field binaries, it would be just 10 to the minus 15 to 10 to the minus 17 per second. For globular clusters, it could be 10 to the minus 16 to 10 to the minus 12 per second. And your SMBHs, it could be 10 to the minus 10 to 10 to the minus 6. This is just because the compactness of the environment becomes more and more as you go down the list. Right. So supermassive black holes, really high acceleration in the galactic field, not so high. Right. So now you can actually estimate the acceleration from 170817 and 190425. So GW 190425 is another binary neutron star event, which these are the only two binary neutron star events that we observe, and these are ideal for this measurement since they are low mass events. They stay in the band of the detector for a long time, and hence you can measure this dephasing and this acceleration as a function of time better. And as you can see, no surprise, both these measurements are consistent with zero acceleration, and you have like roughly an upper limit on the acceleration, which is roughly, for the case of 170817, it's roughly 10 to the minus 6, and for the case of 190425, it's roughly the upper limit on A by C is 10 to the minus 5%. Right, and if you have if you have a binary near a 10 to the 10 supermassive black hole, which is difficult to get, I guess, but 1 parsec away from a 10 to the 10 solar mass supermassive black hole, you have an acceleration of about 4 times 10 to the minus 12. And so you can just use basically this formula. You can plug in the upper limit of acceleration into this formula and constrain that the distance of GW17 or 17 from the center of its host galaxy was greater than 12.1 astronomical unit. And this uses the fact that we know the mass of the supermassive black hole nearest to 17 or 17, and we know this because we actually had localized it to the host galaxy. This 17 or 17 had an electromagnetic counterpart using which we could actually localize, point it to which host galaxy it came from. But this constraint is extremely weak, since we also know the precise location of 17 or 17 with respect to the SMBH in that galaxy, and it was roughly 2 kiloparsec away. So it was very, so there's like a huge,
What's the force field radius of a 10 billion solar mass
it's
in AU?
10 billion solar mass black hole?
Well, so your scale, right?
Yeah.
10 to the 10.
Oh,
A
yeah.
couple AU.
Yeah.
Oh, 10 to 8 solar masses is a couple AU.
Yeah. So this is just like a formula just for illustrative purposes.
Right.
Yeah.
What if you have a constraint on the radius being bigger than 12 AU?
Yeah.
If we know that it's external to the supermassive black hole, it's 12 AU bigger than the force.
Yes, it's roughly like 6 structural radii or something for the supermassive black hole, 17 or 17. Yes.
But if one applies the additional constraint that the binary has to start inside its build radius, what is the constraint on the merger time?
What's the constraint on the merger time?
Yeah, because it has to be close enough. The
Yeah.
two black holes have to be close enough that they will not be torn apart by the tidal field. Big
That's
black hole,
Yeah.
which then constrains the merger time.
Yeah. So from what I've not looked into that, but from what
that's if the merger time turned out to be really short,
Yeah.
then the scenario is disfavored for another reason, because then you have to make that black hole
Exactly.
happen, soon before you would actually see the merger.
So things like this are basically highly debated in the community right now. For instance, you can also, people think that there might be these migration traps around supermassive black holes, and which forces cancel out, and they could just merge at the place that were formed basically. So there are all these issues in the community, and
No, but if you want a detectable signal right now, then you have a tighter constraint.
Yes, that's right. But even from models that basically run simulations of binary neutron stars in say AGN-like scenarios, they do say that the merger rate of binary neutron stars in AGNs is really, really low. So it's not surprising that we don't see things around supermassive black holes so far. So even from the theory side, it's not at least for binary neutron stars, it's not really favored that things would really be around supermassive black holes, but of course binary black holes could be around supermassive. And similarly for 190425, we have a similar constraint. I will not talk about that too much and move on to my next slide. So this is basically constraints on basically the measurability, or you can think of this as the minimum measurable acceleration that a binary can have if it needs to be measured by 3 different scenarios. So this is the 05 scenario, which is basically the state of the LIGO-Virgo detectors about 5 years from now. And these 2 are future scenarios that I mentioned at the really starting of my talk. This is from Cosmic Explorer, and this is Einstein telescope. So as you can see, as I make my detectors better, of course, the measurement of, I can measure lower and lower values of acceleration. For instance, in this Einstein telescope-like scenarios, if binary neutron stars are roughly have accelerations of about 10 to the minus 9, I can measure them. And even binary black holes, if they have accelerations of about 10 to the minus 6, I can measure them. Which means if say you take a rough scenario where you have a 10 to the 8 solar mass black hole, if things are within say 10 to 1000 structural radii of the supermassive black hole, I can actually measure that with these proposed next generation ground-based detectors. However, if you have a decihertz detectors, again, these are in planning stages and so on, decihertz meaning it operates as a 10 to the minus 1 hertz regime, these would have really long inspirals for these binaries. And because you have long inspirals, you can also measure the acceleration better. And you can go down to, especially for binary neutron stars, you can constrain about 10 to the minus 16 per second. So for context, if 17 had happened when Desigo was on and Desigo was operating at its design sensitivity, you could actually say that 17 was about 2 kiloparsec, or was, roughly 2 kiloparsec from the center of its galaxy, without really observing an electromagnetic output. So that's the real power of this thing, that you can actually tell that you can start to probe the formation environments or the merger environments of these binaries without actually localizing them on the stack. So this is just a nice cartoon to end things. What I've plotted is accelerations in the Milky Way, so you should just really look at the orange line. These are accelerations in the Milky Way as a function of radius from the center of the Milky Way. As you can see, so of course acceleration decreases as you go out far into the edges of the Milky Way. So you can probe, accelerations about 10 to the minus 9, 10 to the minus 10 with next generation detectors, next generation ground-based detectors, which translates to roughly 10 to the minus 5 kiloparsec or 10 to the minus 2 parsec from the center of the black hole or the center of the galaxy. But with Desigo, you can actually start probing a few kiloparsec from the center of the galaxy. So this is the real power of this method if we have a detector like Desigo on.
So in the Desigo range, how long does the crosshair binary last?
So about anywhere from a few months to a few years. So what we assumed here is that it's like we only chose those binaries in the calculation which lasted for less than 4 years in the band, just because at least at the time when it was proposed, Desigo was supposed to run for 4 years. Okay.
Got to build it.
Yes, got to build it. This is just another project that a student that I worked with did, where we took all the simulations that, for instance, Claire does, this cluster Monte Carlo simulations of globular clusters, and tried to find out what the accelerations of merging binaries in those globular clusters were. And basically, this is the histogram. So this is the blue dotted line is the total histogram of all sources, of all accelerations, whereas this orange line is the histogram of found accelerations, the one that we can detect. And as you can see, any accelerations about roughly 10 to the minus 16, you can detect. Okay, so I'll quickly end. So acceleration can be measured with gravitational wave events. This is not trivial because it changes a quantity that we actually observe in the detector, namely the detector frame chirp mass. And we can, hence, because the detector frame chirp mass actually varies with time, when you have an acceleration, you can actually measure it with gravitational wave events. The best constraints come from low mass events. Accelerations measured with 17 and 19/25 are consistent with 0, no surprise. Future detectors would measure accelerations with very high precision and hopefully probe formation environments of binaries. And the future work is, apart from measuring acceleration, you can also try to measure higher derivatives of acceleration, jerk, snap, crackle, pop, etc., whatever. But basically, the really cool thing about that is when you measure acceleration, you're sensitive to gm over r squared, or in other words, omega square r. But when you have high derivatives of acceleration, you're sensitive to omega cube r, omega raised to 4r, and so on and so forth. Which means if you can measure all these things independently, you can actually now try to measure the mass and radius independently. So this is the mass of the environment that the binary black hole is in, and the radius from the center of that environment independently. So stay tuned for the results. I'll hopefully talk about it at some point. And thanks for listening. Thank you.
Thanks for the talk. That was very interesting.
Can you say a little bit more about how you distinguish the acceleration of the binary, like the source binary, the Earth's acceleration?
No, we actually don't account for that here at all. So we assume that, basically we assume that the Earth is zero acceleration, which at least I think might be an okay estimate, because the Earth is about 8 kiloparsec from the center of the Milky Way, so the acceleration is really, really low. So especially for the environments that we want to measure accelerations in, that component is negligible.
It's being accelerated by all the planets and so on.
Yeah, but even that, for the acceleration, it's still very low. Like if you if you sort of try to calculate what the contribution of those things to the Earth's acceleration is, that's relatively low. I mean, it's still of the order of that number. However, if you ask what the acceleration of the jerk and the snap and the crackle and the pop is, that will be a problem. So that's one thing that we are struggling with right now, because those would be systematics for the measurements of the higher derivatives.
Wait a minute, as regards present generation of detectors, that might be, but for Vesica,
Yeah.
the limits you're talking about there.
Yeah.
It's like the acceleration of the Earth by Jupiter is what? It's going to be of order 1 in CGS.
Is it? Okay. Okay.
2 times 10 to the 30. Oh, no, there's a factor of units constant.
Yeah, G by basically G. Is that what you call it?
Yeah, okay, it's 10 minus 6, 10 minus 7.
Uh-huh.
Still
Yeah.
pretty big.
Yeah. So yes. So for Desigo-like detectors, we will have to take those effects into account.
Okay.
We don't take it into account
You're
in this.
measuring massive Jupiter, it sounds
Yeah, I guess. Especially if you start measuring the jerk and the snap, etc., because those will have contributions from omega cube and omega to the 4. So that's a higher contribution to the whole total measurable quantity. So yeah, especially for those things, we'll have to correct for motions of planets in the solar system and stuff like that. Yeah. So it's a pretty complicated measurement in Desigo, but the fact that we can do it is great. Do you have a follow-up?
We should talk about this more, but I think you might be able to use the whole catalog, because the whole catalog, like let's say you have things causing a different
Right.
they'll have different intrinsic acceleration, but they'll share the same Earth acceleration.
Right.
Sort of how PTAs have like a common Earth.
Correct.
But we can
Yeah.
talk about this offline.
Yeah, I see your point. Yeah. Any other questions?
Are there more questions? No? We're ready for a good discussion. So let's begin. So thanks, Aditya, for the seminar
Thank you so
again.
much. Yeah.
And nothing